Welcome students. We will begin our class at 6:02 p.m. So we'll wait for 2 minutes for other students to arrive. Okay, so let us start our today's class. So welcome to Module 5. In today's class, we'll be basically looking on first order circuits, that is basically RC and RL circuits. So let us start our class for today. So in the previous classes, we have already covered the network theorems. So in today's class, we'll be looking at RC circuit and RL circuits. So we can classify today's topic in 4 groups. So that is, first of all, we'll see some RC circuit. Those are self-excited RC circuits. That is, there will be no external source applied. That is a simple RC circuit connected in series. And then we'll be looking at RC circuit with external excitation. So that is the effect if any other source, basically a DC source, is connected. And similarly, in case of RL circuits, we'll again see the self-excited circuits. And finally, RL circuits with an external source. So let us start. So first of all, we will see RC circuit. So I'll give a brief introduction about this RC circuit and the important formulas required to solve some problems. So RC circuit consists, as the name suggests, consists of a resistor which has to be connected in series with a capacitor, where the resistance is denoted by R and the capacitance by C. And since this is a self-excited circuit, therefore at time equals to 0, that is t equals to 0, the capacitor is already charged. So let us suppose the charge on capacitor being V0. So the charge on the voltage drop across the capacitor is V0 at time t equals to 0. So we can say that Vc is equal to V0 at time t equals to 0. So we already know that the basic property of a capacitor is to get discharge with respect to time. Since there is a resistor connected, so a resistor can also be represent a load. So since there is a load connected across the capacitor, it will soon start to discharge as the circuit gets completed. And we already know the plots. So initially, suppose along x-axis we have time, and along the y-axis we have the voltage across the capacitor Vc. So voltage here across the capacitor we are denoting by Vc, which is a function of time. So at t equals to 0, since the capacitor is fully charged, we'll denote this by V0, and slowly the capacitor will start to discharge, and the nature of discharge will be an exponential curve. So I will not go into the derivation. You can look into the assignment and coursework. So in that you have already gone through the derivations. So we get the function of this discharge curve, that is Vct, is given by V0, and there is exponential decay, that is by a negative sign, t by tau, where tau is the time constant, and tau is also given by Rc, where R is the resistance and C is the equivalent capacitance of the circuit. So let us move ahead. So we already get the discharge function for a capacitor, that is self-excited circuit. So now suppose if we have a source connected here, so I'll draw the circuit quickly. So we have a source of voltage V, and the polarities are given as below, and there is a resistor R connected across the source along with a capacitor C. And again in this case we can denote the voltage across capacitor as Vct. So there are two cases here. So the first case will be case 1, that is when the capacitor is already discharged, that is this is an uncharged capacitor, it doesn't hold any coulomb of charge. So in that case a capacitor at t equals to 0 will behave as a short circuit, that is the current there will be no potential drop across the capacitor, but soon as t progresses, that is t0 plus, the capacitor will start to charge and a voltage will be start to develop, that is Vct. A voltage across the capacitor will start to develop. And similarly the expression for the voltage across the capacitor Vct is given by V0. So V0 is the source here, and multiplied by 1 minus e to the power minus t upon Rc, where Rc is the time constant of the circuit. So if we draw the curve, so again on the x-axis we have time, and along the y-axis we have Vc, that is the voltage across the capacitor, and suppose this is V0. So in that case the voltage at suppose t equals to 0 will be V0, and soon the capacitor will starts to discharge, and finally we'll see the capacitor getting charged. In case if we connect the circuit, the capacitor will be getting charged, and the final voltage across the capacitor Vc at t tends to infinity will be V0. So we can say that if I use the different color, so this will be the voltage curve for Vc, that is at time equals to infinity, very long time, the voltage drop across the capacitor will be V0. So let us solve some problems related to these. So the first problem here, in the given circuit, the capacitor has already been charged and the voltage drop across the capacitor is given 15 volts. So we have to find the potential drop across the capacitor, that is the function of discharge, how the capacitor will discharge. And also in the question we have to calculate Vx, and Ix, that is the current flowing through the 12 ohm resistance, and the voltage drop across the 12 ohm resistance. So since initially the capacitor is fully charged, so the potential here they have already provided that V naught across the capacitor is given as 15 volts. Okay, so we have already covered the Thevenin's rule. So since we are working across the capacitor, so we need to find the Thevenin equivalent resistance across these nodes A and B, since the capacitor is connected across A and B. So the Thevenin resistance RTH, I will wait for a minute. Please tell me what will be the Thevenin's resistance across the nodes AB. So it's a simple straightforward calculation here. So as we look from points A and B, we have to find the equivalent resistance of the circuit. And for the time being, let us ignore the capacitor. Assume that there is no capacitor present between A and B. There is an open circuit between point A and B. So as we see from point A and B, we can say that 8 ohm resistor, this 8 ohm resistor and this 12 ohm resistor are connected in series, and finally the sum of these two resistance, the equivalent resistance, is connected in parallel to a 5 ohm resistor. So the Thevenin's equivalent resistance here will be 8 ohm plus 12 ohms that are connected in series and both in parallel with a 5 ohm resistor. So this will become 20 multiplied by 5 divided by 20 plus 5. So that is 25. So 5 times 25 and 5 4s are 20. So the equivalent resistance RTH, we are getting 4 ohms, and we know that time constant tau is given by RC. So the resistance R here is 4 ohm and the capacitance is already given 0.1 farad. So this will become 0.4. So a quick question, what will be the unit of time constant? Please write down your answer in the chat box. What will be the unit? So can anyone please define what is time constant, tau? Okay, so the unit for time constant will be second. So time constant is a value at which the circuit gets 1 by E times discharged. So suppose if we have a voltage curve, so the time required T at which the voltage V gets discharged by a factor 1 by E, that is around 36%. So this value along the x-axis is called tau, and the unit will be of time, that is seconds. So now we have already calculated the time constant tau. So tau is 0.4 seconds. So now we know the discharge function of a discharge curve. We already know derived the equation for this discharge function. Not derived, just revised the concept that at what rate the capacitor gets discharged. So the formula for the voltage across capacitor is given by the voltage V naught, that is the charge voltage at time equals to 0, multiplied by epsilon. There will be a multiplied by exponential function E, and the decay, this is a decay function, there is a negative sign, T by tau. So V naught is given in the question 15 volts, and we have just calculated tau as 0.4. So therefore this will become 15 e to the power minus 2.5 t. So this will be the voltage drop across the capacitor. Okay, so if any doubt, please you can ask any question. How we arrived with this formula. And so the first part of the question is VC. We have already calculated VC, which is exponential function. I will just draw the function, how it will look. So at time equals to t equals to 0, this will be 15 volts, and slowly the curve will starts to voltage starts to decay exponentially as a function of exponential function. So I'll again ask one more question. So here, suppose if we increase the value tau, that is the time constant, so how will the curve look like? So suppose we have two curves here, one already drawn and another curve here, I am drawing it by green. So suppose the blue one has a time constant tau 1 and the green one has time constant tau 2. So which will be higher? Tau 1 will be higher or tau 2 will be higher? Please write your answer. So option A is if tau 1 is greater than tau 2, option B is tau 2 less than tau 1. Sorry, that both the options being same, tau 1 less than tau 2. So anybody? So the blue one I am saying is tau 1 and the green one is tau 2. So the answer will be that lower value of tau means we can easily reach the steady state faster. So therefore tau 2 is smaller than tau 1. So option A is the correct option. That is for low values of tau. So at low value of tau, we reach steady state faster. Okay, so let us move to second part of the question. So in the second part of the question, we have to calculate the voltage drop across 12 ohm resistor, that is Vx. So we have to use the voltage division rule here, voltage divider rule. So we'll just use the voltage divider rule to calculate the voltage drop across the 12 ohm resistor. So since the voltage drop across both 8 ohm resistor and 12 ohm resistor is Vc, and we had just calculated Vc, so the value of Vc was 15 e to the power minus 2.5 t. So I'll keep that value for Vc. So the value of Vc is given, we have just calculated, and now we have to calculate the value of Vx across the 12 ohm resistor. This will again be a function of time, and so using the voltage divider rule, so across a 12 ohm resistor, so in the numerator we'll have 12 ohms, and in the denominator we'll have the sum, that is 8 plus 12, 20, and multiplied by Vct. So this will become 12 by 20, and Vct is 50 e to the power minus 2.5 t. So this will become 3, 4 and 3, so 9 e to the power minus 2.5 t. So Vx, the voltage drop across the 12 ohm resistor, has also been calculated here, that is 9 into e to the power minus 2.5 t. And the third part of the question, that is you have to calculate the current that will pass through the 12 ohm resistor. So again we can use the simple Ohm's law to calculate the current Ix. So the current Ix will be voltage drop Vx by the resistor 12 ohm. So that will be 9 by 12 e to the power minus 2.5 t. So 9 by 12 will come 9 by 12 0.75. So 0.75 e to the power minus 2.5 t will be the current as a function of time, and the units will be in amperes. So finally we have calculated all the three quantities, that is VCT, that is the voltage drop across the capacitor, then the voltage drop across the inductor of 12 ohm, and finally the current passing through the 12 ohm resistor. So I'll just write the units. So the voltage will be in volts, these two quantities are volts, and current is in amperes. So this was a simple and straightforward answer with time constant of 0.4 seconds. So let us move to the next problem. So the next topic is RL circuit. So just we discussed the RC circuit, now we'll move on to RL circuits. So again in RL circuit we will have in two cases. First case will be charged inductor. So let us first discuss the first case. In that we have an inductor which is charged inductor. So let us say we have an inductor with inductance L and the resistance R is connected across the inductor, and suppose at time t equals to 0 the inductor there is some current I0. Okay. So now again in similar case, a capacitor is a device which stores charge and therefore there is a potential drop across it, whereas an inductor stores magnetic fields and therefore there is a current which it can induce. So therefore the inductor stores some current I0 which can be mutually induced, that we'll see in mutual inductance section. So let us focus now in this problem. So again, since there is a current associated with this device, so we'll be plotting the graph for current I in the circuit, and therefore at time at t equals to 0, since the inductor has full charge, so therefore the current will be I0, and gradually as with time the inductor will discharge. Now in this case again the relationship will be simpler, as similar to the capacitor, but here instead of voltage we have current I of t. So I of t will be a exponentially decaying function e power minus t by tau. Now can anyone tell what is the value of tau here? Please write in the chat box what will be the value of time constant tau. So time constant tau is a value at which the current has decayed to I0 by E, which is basically around 36%. So this value tau, what will be the value of tau? Yes, so the value of tau will be L by C. So we don't have any capacitor connected here in the circuit. Please write your answer. So since this is a RL circuit, we'll be looking right now looking in the first order circuits. So the time constant in case of RL circuit will be L times R, and the units will be in seconds. So I will become I0 e to the power minus RT by L. So this will be the function that we will be using here in case of self-excited RL circuits. Okay. So now the second topic will be, if suppose we have a source already connected. So let us say we have a voltage source of voltage Vs, it is a source, there is a resistance R, and we have a inductance L. So again in this case, at time t equals to 0, since the inductor is initially fully uncharged, there is no magnetic field developed in the inductor, therefore the inductor will behave as an open circuit. So since the inductor will be an open circuit, what will be the voltage drop across the inductor? So since the circuit is open circuit, the current at time equals to 0 will be 0. Okay, and what will the voltage? So since this is an open circuit, there is no current, no voltage drop across the resistor R. Therefore, the voltage at time equals to 0 will be same as the voltage of the source. Okay. So again in this case, we can write the expression for current, decay in the current, I of t. So I of t will be Vs by R, that is the source, divided by R. Since the final current through the inductor at t tends to infinity, it will be a short circuit. So therefore, the voltage source will be directly connected to the resistor, since this will become a short circuit. So V and R, so the current flowing through this loop, I, will be Vs times Vs divided by R. So that is why I of t is Vs by R, and the component for the inductor we can write, since there is an inductor associated here, and suppose the inductor is having initially, instead the inductor is having some current I naught. Let us say I naught is the current at t equals to 0 for an inductor with some certain charge. It is associated charge I naught. So in that case, it will be I naught minus Vs by R into e to the power minus t by tau, that is R by L. So a quick formula here to remember is that I of t is voltage at infinity. That is, if the circuit has been closed for a long time, the inductor will behave as a short circuit, and therefore the current flowing through this circuit at infinity, plus the current initially at t equals to 0 minus the final current I at infinity, and this whole term multiplied by t by tau, that is R by L. So this is a general formula associated with a RL circuit. So let us move to some problems associated with this. So for the given problem, the initial current that an inductor has is 10 amperes, and we have to calculate IT, that is the current drop in the inductor through the inductor, and also we have to finally calculate the current through the 2 ohm resistor. So to see here, we have a dependent source here, that is a dependent voltage source in the right of the circuit. So this is a dependent voltage source. So the rule for dependent source is that we have to externally excite with some independent sources. So let us remove the inductor here first. So I will draw the circuit for this case. So we are exciting it with a voltage source, suppose with a voltage source of 1 volts, and we have a resistor connected in parallel, and so this is a 2 ohm resistor, a 4 ohm resistor, and there is also a dependent source 3I, and I is denoted by, the direction of I is inwards of the current of the voltage source. So here we have 2 loops. Loop 1, let us say I1 current flows through loop 1, and loop 2, let us say I2 current flows through loop 2. So let us write the KVL for both the loops. So -1 plus 2 times I1 and again 2 times I2 is equal to 0. So I1 plus I2 is equal to 1 by 2. So this is equation number 1. And similarly in the loop 2, we'll write minus 3I plus 4 times I2 plus 2 times, here the direction of current I1 and I2 are same, so I will write as common, 2 common, I1 plus I2 is equal to 0. So also we know that here small I is opposite of I1, so I is equal to minus I1. So we'll substitute this I equals to minus I1 here. So this will become minus 3I, so minus minus plus 3I1 plus 4I2 plus 2I1 plus 2I2 equals to 0. So let us simplify this. So this will become 5I1 and 6I2 is equal to 0. So this will be our equation number 2. So now let us solve both the equations. Okay. So let us substitute I2 in equation number 2. So this will become 5I1 plus 6 into I2 we can write 1 by 2 minus I1 is equal to 1 by 2. Is equal to 0. Is equal to 0. So 5I1 plus 6 times 1 by 2 minus I1 is equal to 0. So this will become 5I1 minus 6I1 plus 3 is equal to 0. So I1 become 3 amperes. So I1 has become 3 amperes. That is, this I1 we have calculated it to be 3 amperes. So the we have to calculate the resistance. That is, resistance will be V by I. So this is also known as Thevenin resistance, as is V by I. So voltage we applied 1 volt source and the current is coming 3 ampere. So 1 by 3 ohms is the resistance, Thevenin equivalent resistance when we are looking from these 2 points A and B. So now we have the resistance calculated. So we can calculate the time constant for the circuit. So the time constant tau is L by R. L is given 0.5 and R is, we have calculated 1 by 3. So what will be the time constant for the circuit? Tau. Anyone? Has anyone calculated a time constant? Simplified this relation. So this will become 1 by 2 and the 3 will go upwards. So this will become 1.5 seconds will be the time constant of the circuit. And now we have to calculate the current IT across the inductor. So the current IT is given by the total current that is I naught is into exponential decay minus T by tau. So I naught here is already provided in the question. The inductor is having current flowing through the inductor is 10 amperes. So I'll substitute 10 here and e to the power minus T by tau. So tau we calculated 1.5 or 3 by 2. So the 2 will come up and the 3 will be in the denominator. So this will be simplified to 10 e to the power minus 2t by 3 amperes. So this will be the current, function for current. So now let us calculate the other current, that is Ix. That is the current flowing through the 2 ohm resistor. So we have already calculated that the current flowing through the 2 ohm resistor was, we took two loops with I2 and I1 in this manner. So the total current through the inductor will be I1 plus I2. So I'll just clear some space here. So we have already got the relation for I1. So this is I1 and I2 is given by the expression 1 by 2 minus I1. So I2 will be 1 by 2 minus 10 e to the power minus 2t by 3 amperes. So this is I2, and finally we will get the current through 2 ohm resistor as I1 plus I2. So we have to just add these two. So let us call this as 2 and this as 3. So let us add 2 plus 3 here, equation 2 plus equation 3. So this will come out to be 1 by 2 minus 10 to the e to the power minus 2t by 3 and plus 10 into e to the power minus 2t by 3. That is simply 1 by 2. So the current is 1 by 2. That is a constant current here is flowing through the resistor. Okay, so let us move to the next problem here. So in this problem, we are already seeing some source. So this is a problem associated with a RC circuit with an external source. So the question they have said that at time t equals to 0, the switch moves from A to B. So initially the switch was at position A, and at time t equals to 0, the switch has been moved from point A to point B. So let us first of all draw the circuit for time t being less than 0. So here at time t equals to 0, the transient is happening. So let us first of all focus before time t equals to 0. So I'll just simplify the circuit here. So this is a 24 volt source and a 3 ohm resistor, 3 kilo ohm resistance is here, and a 5 kilo ohm resistance is here, and in parallel we have a capacitor of 0.5 millifarad. So since the for a long time the circuit was in this position, therefore the capacitor will get to start to charge, and finally it will become open circuit. So we have to first of all calculate the potential across the capacitor at time t equals to 0. So that is at time t equals to 0 minus, that is just before the switch has been moved from A to B. So the voltage across the capacitor VC will be the same as the voltage drop across the 5 kilo ohm resistance. So we'll use the voltage divider rule here again here. So the voltage drop across 5 kilo ohm, so it will be the numerator and divided by the sum, since both circuits are in series. I am not simplifying the kilo ohm part because the kilo ohm will cancel out, times the total source, that is 24 volts. So that is 5 by 8 into 24, this will become 15 volts. So at time t equals to 0 minus, the voltage across the capacitor is 15 volts. Okay, so we'll use this information from the first part of the problem to use in the second part, that is when the circuit has been close to B, point B. So now we'll look at the switch when the switch position is at point B. So in that case, the circuit will look like this is a 0.5 millifarad capacitor, and now the circuit is connected to the 4 kilo ohm resistance, and external source of 30 volts is connected here. And we have also calculated that initially the charge across the capacitor, so the polarity here is again important. So polarity is marked here, that is VC at time 0 is given as 15 volts. So now let us use the formula that we already discussed earlier, that is the voltage across the capacitor as a function of time is voltage at infinity plus the voltage at time 0 minus voltage at infinity times the exponential decay function t by RC. So for that we need to calculate the value of time constant RC here. So let us calculate that RC first of all. So RC here will be, so since we are looking in this circuit, here in this circuit there is a resistance of 4 kilo ohm and an inductor of 0.5 millifarad is there. So the RC will be 4 kilo ohms multiplied by 0.5 millifarad, that is 2 seconds. So 2 seconds will be the value of RC. So I am writing here RC, that is tau is equal to RC is equal to 2 seconds. So now we'll just substitute the values here. So V infinity, so what will be the V infinity? So since V infinity, there is an external source of 30 volts, so finally the charge across the capacitor has to go to 30 volt. So V infinity will be 30, and V0 we have calculated 15 minus 30 e to the power minus t by RC, that is 2. So this is 30 minus 15 e to the power minus t by 2. So this will be the voltage drop across the capacitor. So in the question we have to calculate the values at different time steps, that is at time equals to 1 second and at time equals to 4 seconds. So let us calculate that. So at time is equal to 1 second, that is t is equal to 1 second, VCT will be, so VC1 will be 30 minus 15 e to the power minus 1 by 2. So just simplify the value, use your calculator. So 30 minus 15 times exponential to the power minus 0.5. So this comes out to be 20.9 volts, and at 4 seconds this will be 30 minus 15 e to the power 4 minus 4 by 2, that is 30 minus 15 e to the power minus 2. So this is 30 minus 15 times e to the power minus 2. So this comes out 27.96 volts. So you can see that here the voltage is gradually increasing. So if we draw the voltage curve here, so the voltage curve should look like that. At time equals to 0, we have 15 volts. So if you can substitute here in t equals to 0, this part will become minus 15. So 30 minus 15 will become 15 volts. And gradually at t equals to, suppose here in the x-axis we have time. So it will starts to charge. So this will look like this, and finally this will become equivalent to 30 volts. So this value will become this steady state 30 volts. So this is be the typical curve for a charging of a capacitor. So hope this problem is clear. So let us move again to next problem. So this is a RL circuit with an external source. So before moving to the problem, I will just ask one question. If you have any idea, please tell. So till now we have studied RL and RC circuit, but suppose if we directly connect a voltage source to a inductor. So suppose an inductor with inductance L and a voltage source of Vs. So can anyone tell me what will be the voltage and current across the inductor? So there is no resistor. We are assuming that these wires are superconducting in nature and there is no potential drop across these wires. So in that case, what will be the nature of the voltage and current across the inductor? So what will be the voltage VL as a function of time, and what will be the current I as a function of time? Okay, so in case when we are connecting a voltage directly to a inductor, we know the relation that a voltage drop across the inductor V is given by L into the differential change in current with respect to time. So here the voltage is constant. We are applying constant DC volt. So the voltage is Vs. So let us integrate both sides. So Vs dt integral is equal to L integral di. So since since we have a DC source applied here, so integral of a constant will be Vs times time t is equal to L into current IT. So the profile for current will get IT is equal to Vs time divided by L times time. So this will be the profile for current. So as you can see from this relation, we can say that the current in the circuit will at time equals to 0, this will be 0. So along x-axis we have time, along y-axis we have I. So at t equals to 0 it will be 0, and similarly this will linearly increase. So as time moves on, the current through the circuit will move, and so if we reach a very high value of time, the flow of current through the inductor will be very high, and since a very large amount of current will be drawn, so therefore no inductor has a is ideal inductor, therefore it will have some resistance R. And since we know that from Joule's heating, I square RT, as the high amount of current is being drawn and it is again being squared. So if we connect an inductor across a DC source, it will draw a huge amount of current, and finally this will generate a huge amount of heat, that is I square RT, and finally this will lead to burning of our inductor. So we never connect an inductor directly across a potential. Always we have to connect a resistor so that we can limit the amount of current flowing through the inductor. Okay, so let us now move to the problem. So in this problem, the question we have been given with a circuit, and we have to calculate the total current flowing through the circuit as a function of time. So at t equals to 0, there was a short circuit across the 3 ohm resistor. So let us calculate the current flowing through the inductor at time when time t is less than 0 or just before the switch is being opened, that is at t equals to 0 minus. So at 0 minus, I will just simply draw the circuit to avoid any confusion. So there is a 10 volt resistor, 10 volt source connected across a 2 ohm resistance, and there is a short here. So there is no 3 ohm resistance here, since the current will flow through the least resistive path. And finally we have an inductor of 1/3 henries. So since inductor will behave as a short circuit here, since the circuit has been in this position for a long time, so the current at time equals to 0 will be 10/2, that is 5 amperes. So we have calculated I naught at time equals to 0 as 5 amperes. So now let us write here that I at time equals to 0 is equal to 5 amperes. Now we'll move to the again second part, when the switch has been opened. So when the switch has been opened, in that case we'll be having a 10 volt resistor, a 10 volt source, and a 2 ohm resistor, and a 3 ohm resistor will be also there, and finally a inductor of 1/3 henries. So let us first of all find the time constant for the circuit, tau. So can anyone tell what is the tau for the circuit? So this is a RL circuit. The time constant for a RL circuit is given by L/R. So L is given here 1/3 henries and R, so the Thevenin resistance across the inductor by removing the short circuiting the voltage source will be, since these two resistance are in series, so therefore the RTH will be 2 ohms plus 3 ohm, that is 5 ohm. So the RTH I'll substitute here as 5 ohms. So this will become 1/15, that is the voltage, that is the time constant of the circuit, 1/15 seconds. So let us write down tau is 1/15 seconds, and I naught has been 5 amperes, and now we have to find the current at infinite. So at infinite time, that is very long time, so the inductor will behave as a short circuit. So I will just remove the inductor here, and this inductor will start behaving as a short circuit at time tends to infinity, that is a very long time. So the current at I infinity will be voltage times the total resistance, that is 5 ohms, that is 2 amperes of current will be flowing through the circuit. So now we have all the three values here. We have the current at initial stage, I naught, I0, 5 amperes. We have the time constant here, 1/15 seconds, and we also have the final current, that is I infinity. So the relation here is for current through the inductor, the simple relation that we already discussed is given by I of t is equal to I infinity plus I0 minus I infinity e to the power minus t times tau. So this is a relation. So we have to just substitute the value and get the current. So please substitute the value and finally get the answer. So substituting the values, I infinity we got as 2 amperes, so replacing by 2 plus 2 minus 5 e to the power minus t times tau. Tau is 1 by 15. So this will become 2 minus 3 e to the power minus 15 t. So this will be the current flowing through the inductor for t equals to 0 onwards. So suppose if we want to look at how the waveform for the circuit will look like. So we have already calculated the function for current. So suppose at time t equals to 0, if we substitute t equals to 0, the current at 0 will come out, will be 2 minus 3. E to the power 0 will be 1, so 2 minus 3, it is minus 1 amperes. And suppose if you have to calculate at t equals to 1 second, so at 1 second, again we will substitute at 1 second, it will be 2 minus 3 e to the power minus 15. So just put the numbers in the calculator and get the value, what will be the current at 1 second. So we'll take one more point here and try to plot how this curve looks like. So 2 minus 3 multiplied by e to the power minus 15. So the current here will be 1.99 amperes. So it was initially negative value minus 1 ampere, and suppose let us take one more point here, I at 3 seconds. So 2 into 3 e to the power minus 45. So again this quantity will be very small value, so this will reach to around 2 amperes at steady state, since the at infinite portion, infinity, this term will vanish out, because this is exponentially decaying function. So since the exponential part as time increases will reach out to 0, so this part can be cancelled. So at a steady state we will get a current of 2 amperes. So now let us draw the waveform for this circuit. So at time t equals to 0, this was a negative current of minus 1 ampere. So along y-axis we are representing current IT. So this was minus 1 ampere, and at 1 seconds this was 1.99. So let us suppose 1.99 comes out to be here some point, and finally at 3 seconds this was 1.99, and at finally at so this is 0, this is 1, and this is 3. So small rise, a mere rise of 0.01. So if we join all these points, so this looks like this. So this will look like this. So the current becomes steady. This is the way the current flows through the inductor. It becomes steady and this will remain at 2 amperes. So that is all for today. We have seen the first order circuits, RL and RC circuit we have seen, and So we'll be looking for second order circuit in the next class. So I think I have made here a small mistake. So we have calculated the current, and so initially we have taken the formula for the relation here was that I of t is equal to I at infinity plus I of 0 minus I of infinity times e to the power minus t by tau. So just check out that I have used this correct formula because in the answer okay, so here it will be plus. So instead of plus I have mistakenly taken minus, so this will be plus here. So we have to again draw the waveform here. So these values will be slightly modified. So again, since this term is here, it will be 2 ampere and 2 ampere, and at time equals to 0, this will be 5 amperes. At 0, this will be 2 plus 3, that will be 5 ampere. So now the curve will look like at time equals to 0, it will be 5 ampere, and it will be a decaying function where it will stop at 2 amperes. So the curve for this inductor will look like this. That is, it will decay from 5 ampere to 2 ampere under steady state conditions. So that was all for today's class. We have looked for the RL and RC circuit with and without sources. So in the next module, we'll try to look for the second order circuits, that is R, L and C. So what will be the waveform when we have a resistor, inductor and a capacitor both connected either in series or in parallel. So we'll be seeing for both the cases that what will happen if we connect these three components, that is R, L and C, in series and in parallel. Okay, so I will be ending the class for today. Thank you all for joining. Let us see you in the next week. Okay, thank you.